VLSos here. This is a video lesson on exponential modeling. I'm going to imagine that I conducted a scientific experiment. I'm trying to relate two real-world phenomena that I can measure. I can imagine that when I take measurements, I'm comparing the quantity 2 with the quantity 18. And if I conduct the experiment again, let's imagine that I took measurements between two seemingly related phenomena, and I got a measure for one of 4 and the measure of a second for 162. This is very little data, but it's enough to get a model of the situation. A model in this case would be a mathematical equation that contained these two data points. And if I already have some idea that my quantities that I'm measuring might be related as an exponential equation, then I could choose to model my data with an exponent or an exponential equation. That means I'm looking for an equation of the form y is equal to a times b to the x, which means that I'm looking for these quantities that I measured to be compared or to be on the graph or in the equation of an increasing exponential equation. So how can I use my data to complete my mathematical equation? We're going to do it like this. I could imagine getting the measurement of 162, the y value, by putting 4 into this equation. That means that I can draw a version of my model of getting 162 out of a, b to the 4th. And the second data point, I could imagine getting an 18 by putting a 2 in. Or in this case, 18 is equal to a times b when I put 2 in for x. I have two versions of my model, but I don't yet know what the growth factor b is and the initial amount a is. But this is a system with two unknowns. I can use it to solve or find those two unknowns. How do I do that? I'm going to imagine dividing 162 by 18. And if I divided 162 by 18, I've got to do that to the other side. So I'm going to divide ab to the 4th by 18. But I'm not going to divide it by the number 18. I'm going to divide it by what it's equal to. And I know that 18 is equal to this expression. In other words, I can divide these equations, one by the other. 162 divided by 18 is 9. ab to the 4th divided by ab squared is going to simplify quite nicely. The a is a common factor, so it cancels. b to the 4th divided by b squared, I could use the power property of quotient of powers. It's going to be the same base b, 4 minus 2, or in this case b squared. If I square root both sides, then I'll get b by itself is equal to 3. Well, technically both positive and negative 3 because I'm undoing a square. But it doesn't make sense for b, which is the growth factor of my exponential model, to be negative, because then it would be multiplying the negative by the power and it would no longer be exponential. An exponential function has to have a growth factor of greater than 1 to be increasing, or if it's a decreasing exponential model, then between 0 and 1, but not negative. So I know that b is going to be the positive 3. Okay, still need to find a. But if I have b, I can go back to one of my equations, fill in the information that I know. In this case, I'm substituting 3 in for b, and solve for my remaining unknown a. 3 squared is 9, and then if I divide by both sides by 9, I get a is equal to 2, which completes my model. The equation that is exponential that will contain both these points is y is equal to 2 times 3 to the x. Now that I have the model, I could use it as a tool for prediction. So my original scientific measurements were just these 2 points. But with the model, I could say or imagine, what if I made a measurement of x equals 3? What would I expect the y value to be? I could use the equation now to calculate it. One exponential model that we use in science is with the concept we call half-life. Half-life is the idea of the amount of time it takes for something that can break down to break down into half of its original quantity. And typically the context for this is particle radiation. Something like plutonium, which is highly radioactive, will kick out neutrons, and by doing, it'll turn into a different element over time. So radioactive elements have half-lives, which is if you take a lump of it, it's the amount of time it takes to undergo particle radiation, so it literally converts half of its original mass into a different element. The half-life equation is going to have a growth factor of 1/2. So it's like taking an initial amount and then halving it. Let's imagine that we have a substance that we'll call an equation for it, and the equation will calculate the amount of that substance after a certain time t. So if we had 100 or 100% of something, then 1 half-life later, we would have half of it, or 50%. So we can imagine comparing half-lives, the number of half-lives, to the amount of substance that we have. If we are considering a second half-life period of the original substance 100, then it would be half of 50, or after 2 half-lives, we would have 25% of that thing. After 3 half-lives, we'd have 12.5%. We could give p the variable number of half-lives after an initial amount. But the number of half-lives is different than the time it would take for the amount to degrade, because half-lives are measurements of time and not necessarily 1 year or 1 minute. If we consider the half-life, the amount of time it would take to degrade into 50% as being a measurement of 15 years, that means that after 1 half-life, we would have a change in time of 15 years. Or after 2 half-lives, we would have a change in time of 30 years. Now, this is taking the half-life that we can symbolize as lambda, Greek letter, as the amount of time that it takes to degrade. So after 3 half-lives, we will have 12.5% of the original substance, and that will be equivalent to after 45 years. So what kind of equation then calculates the amount after a certain time t? In this case, it's going to be exponential decay. The original amount is 100, or 100%. It is going to have a growth factor of 1/2. And the half-lives then, how many times we take half of the substance, it's either going to be expressed as p number of half-lives. But if we want to convert this into an equation for time, then it's going to be 100 times the growth rate of half times time over 15. So if time were 30 years, then the exponent would be 30 divided by 15 to be equivalent to 2 half-lives, which means the exponent of 1/2 is 2. That would be halving the 100 2 times. And that's how we get to 25. In general, a half-life equation is the amount after time t is equal to the initial amount, a sub 0, times 1/2 to the t over lambda, where lambda is the amount of time of the half-life of the substance.